All right, this one here, we're given a reaction, we're given a K, and we're given initial concentrations. We want to know what direction the reaction is going to proceed, and then we want to know all the concentrations at equilibrium. So we're only given initial concentrations, and we're given K. So first of all, let's write our expression. Write it assuming we're going to the left, but that's okay if we're not. Okay, now this is how we do K. Now, when you're not at equilibrium, or you're not sure you're at equilibrium, you calculate this according to what is called the reaction quotient Q. So in this case, let's calculate Q. C for concentration, I don't really worry about that. But so let's calculate Q. You use the same expression, but you don't know if you're at equilibrium. So 2 molar of each of the products. So that's going to be 2 times 2, and 1 molar of each of the reactants. All right, you can see that that's 4. The next thing we need to do is we need to compare Q to K. Q versus K, Q is greater than K. Now, when Q is greater than K, that means we have too many products. So here we have too many products. So in order to get to equilibrium, the reaction is going to go to the left. However, we're still going to write out our ice table. So let's do that. Let's do it over here. I'm going to write it again. CO plus H2O, CO2, H2. I'm keeping this so I can use this, but we know the reaction's going to the left. Make an ice table. Okay, next. We start with 1 of each of the reactants and 2 of each of the products. Now we said the reaction's going to the left. The reaction going to the left means these are now reactants and these are products. So we're going to be losing these. Copy the coefficients if they're there. These are 1s. And we're going to be gaining these. This is what happens when the reaction goes to the left. So at equilibrium, we don't have any numbers here. So we have 1 plus x, 1 plus x, 2 minus x, 2 minus x. We're going to do some algebra. Next, plug our equilibrium values into K in order to solve for x. So our K value is 1. Now, CO2 and H2, that's 1 plus x, quantity squared, 2 minus x, and quantity squared. Now in this case, things get a little bit easier. You can do this with quadratic if you want to, or you can say, look, everything's squared, so let's just take the square root. 1 plus x over 2 minus x. Solve the algebra here. 2 minus x equals 1 plus x. So we get, let's add 2 equals 1 plus 2x. 2x equals 1, x equals 0.5. So now we have solved for x. What do we do now? Well, we don't need to we solve for x. We don't need k because it gave it to us. We are going to use our x to find all of our equilibrium concentrations. So here, 1 plus 0.5, 1 plus 0 plus 0.5, 2 minus 0.5, and 2 minus 0.5. So in this case, you don't have to show me all that work if you don't want to. Make sure to put your concentration units on at the end. All right. So let's do another one. Here we're going to have a reaction, and we're given a container of a flask, how much it initially has, and how much is at equilibrium. We want to know the equilibrium constant. All right, so the first thing we should do is write an expression for K, because that's what we do. Is going to equal HI squared H2 and I2. Okay, this wants to know Kc, so dealing with molarity. Now we're going to need a little bit of help before we can start this, because we got to be in molarity in order to use this. So we're given masses, so let's do some quick work. You might need your periodic table. 0.763 grams. No, it's not that. It's not. It's 1.08 times 2. So that's what, 2.016. Grams of H2 is 1 mole of H2. And it's in 3.67 liters. I'm going to do these calculations at the end. I'm just going to go ahead and write these out before I start pushing buttons. 96.9 grams of I2 on the periodic table, 253.8. How you round might be different than me. That's okay. That's the volume of the container. The good thing when your gases, everybody has the same volume if they're in the same container. 90.4 grams. So that's going to be 127.9 grams is 1 mole. See, molarity doesn't go away. All right, so now let's calculate these. 0.763 divided by 2.016 divided by 3.67. 0.9 divided by 253.8 divided by 3.67. 0.104. And 90.4 divided by 127.9 divided by 3.67. And 0.193. And how many decimal places you use and round may be a little bit different than mine, but that's okay. All right, so now that we have some concentrations, let's make our ice table. So here we have H2 plus not H2 plus I2 is going to make 2HI. Initial change equilibrium. All right, so initially I have H2 and I2, but I don't put these numbers in. I want to put my concentrations. 0.103, 0.104. Should have made that bigger. Initially, it doesn't say I have any of that, so there's none. All right, and HI, I have 0.193. Okay, now let's see what our changes will be. Here we go from no products to products, so we have obviously gained products, copy the coefficient. We're losing reactants, copy the coefficient. All right, so now solve for x. 2x equals 0.193, so let's divide by 2. 0.0965. Okay. So now let's subtract that. 0.0965, 0.0965. You don't have to write that in there if you don't want to. I'm just showing you where to plug it in if you're not sure. Okay. .104. Okay, 0.0075. All right, this is asking us to calculate the equilibrium constant. We now have concentration, so we can plug those in. Copy them correctly. All right. And there I got 764 for K.